So today we will discuss about Newton's first law of motion. That what is the Newton's first law of motion and how the Newton first law came into being and how Newton first law works. So we will discuss all about Newton first law of motion and details in this video, and I hope you will like this video. So let's start. Before Galileo's time, most philosophers thought that some influence or force was needed to keep a body moving. They thought that a body was in its natural state when it was at rest. For a body to move in a straight line at constant speed, for example, they believed some external agent had to continually propel it, otherwise it would naturally stop moving. If we wanted to test these ideas experimentally, we would first have to find a way to free body from its influences of its environment or from all forces. This hard to do, but in certain cases we can make the forces so small. If we study the motion as we make the forces smaller and smaller, we can get an idea of what the motion would be like if the external forces were truly zero. Let us place our test body, say a block, on a rigid horizontal plane. If we let the block slide along with this plane, we note that it gradually slows down and steps. This observation was used, in fact, to support the idea that motion stopped when external force, in this case hand initially pushing the block, was removed. We can argue against this idea, however, by reasoning as follows. Let us repeat our experiment now using smoother block and smoother plane and providing a lubricant. We note that the velocity decreases more slowly than before. Let us use still smoother blocks and surfaces and better lubricants. We find that the block decreases in velocity at a slower and slower rate, but travels further each time before coming to the rest. You may have experience with an air track on which objects can be made to float on a film of air. Such a device comes close to the limit of no friction, as even a slight up tap on the other sliders can send it moving along the track at a slow and most constant speed. We can now extrapolate and say that if all friction could be eliminated, the body would continue indefinitely in straight line with the constant speed. And external force is needed to set the body in motion, but external force is needed to keep a body moving with constant speed. Let us discuss about the first law and reference frames. So Suppose you are a passenger riding in a car and you are tightly held in your seat by a seat belt. When brakes are applied, a book that was on the seat next to you begins to slide forward. There is no apparent force on book that is pushing it forward, but relative to use it appears to start moving in a violation of Newton's first law. Your friend Bill, who is standing along the side of the road, sees you, the car, but book all moving together, say at 22 meters per second. If you and the car suddenly slows to 20 meters per second, in the absence of friction, with the seat of the book continues to move at 22 meters per hour. According to Bill notices nothing unusual, and detects no violation of Newton's first law. So, the definition that if the net force acting on a body is zero, then it's possible to find a set of reference frames in which that body has no acceleration. The tendency of a body to remain at rest or in uniform linear motion is called inertia, and Newton's first law is often called law of inertia. The reference frames to which it applies are called inertia frames. Okay, so now we will move on and we'll discuss about the inertial references frames and relative motion. Suppose you are in a car moving down a road at 22 meters per second. Your friends in the same car are also moving at 22 meters per second. You could toss a ball sideways into your friend's lap, and the toss is unaffected by the velocity of the car as long as the car continues to move at constant velocity. The ball lands in your friend's legs. If you are passed by your friend Sally, who is in another car moving with a speed velocity of 27 meters per second, you observe the distance between your car and Sally's to increase the rate of 27 meters per second to minus 22 is equal to 5 meters per second. That's relative to your car. Sally's car is moving at 5 meters per second. Take away the external clues, the scenery spreading by, the still air rushing and the moving car, the bumpiness of the road and the noise of the engine, and consider only the two cars. You would have no way to decide which car is really moving. Now let's discuss about force, that what is force and how it works. According to Newton's first law, the absence of forces leads to absence of acceleration. What about the presence of force? Based on the common experience, it is reasonable to assume that a body will accelerate when a force is applied on to it. We now develop our concept of forces by defining it operationally in terms of the acceleration it produces when applied to a chosen standard body. Any object can serve as our standard body as long as it is clearly identifiable and reproducible. For example, We might choose a block of copper or glass of any specified dimension. Before we proceed with this measurement, we must first invoke Newton's first law to check we are working in an inertial reference frame. If the body is at rest, does it remain at rest? If we start and moving with a constant velocity, does it remain in this state of motion? In attempting to answer the second question, you probably will discover that the body, once in motion, gradually slows down due to friction. By careful design of our apparatus, you create a nearly a friction-free environment as we can, perhaps by floating the body on a film of air, lubricating the surface on which it moves. We intend to apply a force to the body and measure its acceleration, and we want to be sure that any other forces caused by environment have a negligible effect on the motion of the body. As the agent that supplies the force, we choose a light spring. We observe that spring come in different toughness, requiring different efforts to stretch them. We also observe that the effort needed to stretch a given spring and increasing as stretch it through larger distances. So that's all about that. Now we will discuss about the mass. What is mass? In the previous section, we discussed a series of experiments that we used to calibrate a set of springs based on the accelerations given to standard body when the spring were stretched to different lengths. Now we want to repeat those experiments to answer different questions. What effect will the same force have when applied to different bodies? Everyday experience leads to guess at qualitatively answer. It is much easier to accelerate a bicycle than a car by pushing it. Clearly, the same force produces different accelerations when applied to different bodies. What makes these bodies differ in our ability to accelerate them by pushing is their mass, which is a property of a body that determines its resistance to change and its motion. Let us see how we can study the relationship between force and mass by accelerating bodies of different masses using the calibrated spring set. We start by obtaining a sound identical standard by body and attaching it to the first body. We then apply 1 unit of force is previously determined from the single body to this combined object, and we observe the acceleration to be 0.5 meter per second. Applying 2 units of force, we find acceleration of 1 meter per second square. We can repeat the experiment with 3 standard bodies joined together, then 4, and so forth. here is a possible set of outcomes of the experiment. So you can see the outcomes of this experiment: acceleration of 1 standard body, acceleration of 2 standard body, acceleration of 3 standard body. This is the units: first unit, second unit, third unit, and fourth unit. So these were all about the mass. So we discussed the first law of motion, and then we discussed the initial references, frames and relatives, and then we discussed the force, and at last we discussed the mass, and what is mass and how it works. So that's all about today. We'll see you in another lecture. Thank you very much.